Okay, I recall that we saw problems with the Mercalli intensity scale. In 1935, Charles Richter devised a procedure to measure the size of the earthquake based on ground motion rather than the amount of destruction. The Richter magnitude is determined by measuring the maximum amplitude of a P or S wave on the seismic wave pattern. And we see this example where we take a baseline and then just simply pick the peak with the maximum amplitude and measure its vertical distance from the vertical height from the baseline. And what's more, this measured amplitude at each of these different seismograph stations must be adjusted to account for weakening of the ground motion with distance from the epicenter. So here is an example of determining the Richter magnitude. In the seismograph record shown on top, in this case we're looking at the maximum amplitude of an S wave. And notice that that amplitude has been measured to be about 23 millimeters in height. What we do then is simply go to the right scale of amplitude and plot that 23 millimeter value as shown in that lower figure. Now we also need to know the distance of this particular seismograph station from the epicenter. And again, how do we determine that distance? Yeah, we look at that time interval between the first arrival of P and S waves, and we see it to be 24 seconds as measured in that seismograph record. So on the scale to the left, we plot that 24-second value as shown. And then from there, we simply draw a straight line connecting those two endpoints. And where the line passes through the middle scale, we can then simply read off the magnitude. In this case, the magnitude is 5. Everybody see that? So here's a table of the earthquake magnitudes, which range from less than 2 up to values in excess of 8. And obviously, the higher the Richter magnitude, the stronger, more energetic the earthquake. And it's actually a logarithmic scale, which means that a magnitude 1 difference in the Richter scale indicates a factor of 10 difference in the overall amplitude of ground motion. So, for example, a magnitude 5 earthquake has 10 times the amplitude of a magnitude 4 earthquake. Okay? Yeah, if you look at the total number of earthquakes, there are well over 600,000 earthquakes that occur globally each year that have magnitudes less than 2. And for the most part, those earthquakes are not really felt. They're simply recorded by sensitive seismograph instruments. But fortunately, the higher the magnitude, the fewer the number of earthquakes per year, so that when we look at magnitudes at 8 or greater, usually less than 1.4 of those occur every year. It'd be pretty bad if it was the opposite. But anyway. Now here's a map showing the region most affected by a magnitude 9.2 Alaskan earthquake back in 1964. This was a huge earthquake, one of the largest ever recorded. And it occurred just to the northwest of Valdez, Alaska. Anchorage, which is quite a bit further west, nevertheless experienced a great deal of damage. Valdez, in turn, also experienced great destruction, mainly as a result of the tsunami that was generated as a result of this particular earthquake. Now, seismologists often prefer a scale that measures the actual energy released by an earthquake. And this is known as the moment magnitude, which depends on such things as the overall amount of slip on the fault plane, as well as the area of the fault break. And this value also takes into account the overall rigidity or strength of the rock. But the total energy of an earthquake can be directly related to its Richter magnitude using the equation log to the base 10 E equals A plus BM, where E is the total energy in ergs, M is the Richter magnitude, and A and B are constants that depend on the local geology. But the point is that you can calculate the actual energy of the earthquake by comparing it to the Richter magnitude. And in this figure, notice that again, in the left scale, we have the magnitude from 2 at the bottom to greater than 9 at the top. Earthquakes of magnitude 9 or greater are the largest recorded earthquakes. And 3 of those occurred over the last few decades. One in Chile back in 1960. This was a magnitude 9.5. The Alaskan earthquake of 1964 was a magnitude 9. And then there was an earthquake in Japan in 2011 of magnitude 9. But if you compare the magnitudes on the left scale with the overall energy release on the shown on the right scale, the energy release is expressed in equivalent kilograms of explosives. And these values literally explode as you go up the scale of magnitude. In general, the energy released by a seismic wave increases by a factor of 32 for each unit on the Richter scale. Here's a map of the distribution of nearly 15,000 earthquakes with magnitudes equal to or greater than 5 over a 10-year period. And we see that most of those earthquakes, as we would expect, occur along plate boundaries. Divergent plate boundaries like the Mid-Atlantic Ridge. We also have convergent plate boundaries that rim the margins of the Circum-Pacific Belt, known as the Ring of Fire. Even transform faults like the San Andreas generate quite a bit of earthquakes in a short amount of time. Here's another map distinguishing whether or not earthquakes are shallow, intermediate, or deep. According to this scale, the blue dots represent shallow earthquakes where the hypocenters are at depths of less than 69 kilometers below the surface. Intermediate earthquakes are those where the hypocenters occur anywhere from 70 to 300 kilometers depth. And then the deep earthquakes range from 301 to about 700 kilometers depth. And the deep earthquakes are indicated by the reds. But just looking at this map, we find that shallow earthquakes, the blue dots, occur along all types of plate boundaries. On the other hand, note that the intermediate and deep earthquakes are restricted to convergent plate boundaries. In other words, all of the plate margins where reds and yellows are plotted, those are all convergent plate boundaries. subduction zones. Now, intermediate and deep as well as shallow earthquakes occur within subduction zones. This particular convergent plate boundary occurs along the Tonga Islands east of Australia. And if you look at the lower left-hand corner block diagram, we see the shallow earthquakes near the surface plotted as blue dots, the intermediate earthquakes plotted as yellow dots, and the deep earthquakes plotted as red dots. Now, for each of these different plots, these are all plots of the hypocenter. These are the sites of initial fault slippage. But to get the epicenters, we simply take each one of these dots and project it up and plot it on the surface. And so the epicenters can be plotted on the surface, and that's shown in the diagram towards the right. And as we would expect, the blue dots, the shallow earthquakes, plot closest to the trench. Further from the trench, we encounter the intermediate yellow earthquakes. And finally, furthest from the trench are the epicenters of the deep earthquakes. And just by looking at the overall distribution of these different colored dots, we know that we can figure out we're looking at a subduction zone. Basically, oceanic lithosphere descending into the mantle at an angle of around 45 degrees. Okay. Here's a map of the distribution of known earthquakes of magnitude 7.5 or greater since 1900, where the largest dots, the large red dots, represent earthquakes of magnitude 9 to 9.5. And the largest earthquakes occurred in places like Sumatra back in 2004. Here's the Alaskan earthquake of 1964, shown at the top, and the Chilean earthquake that occurred in the 1960s. The smaller dots represent earthquakes of lower magnitude going down to magnitude 7.5 to 7.9. But all of these plots occur along convergent plate boundaries, subduction zones. Here's something else we can do. We can determine using seismograph records. Seismologists can determine the actual type of earth fault movement that produced the earthquake by utilizing what are known as fault mechanisms. And this is done by noting the first motion of P waves arriving at seismograph stations. And by noting this first motion, we can determine the orientation of the fault plane and the direction of slip that generated that particular earthquake. This is done by plotting the location of all the different seismograph stations from around the world onto this circular plot shown in this figure. So this can be envisioned as looking at a global, this can be envisioned as looking at a plot of all the seismograph stations around the world. And from here we determine whether the first motion of the P wave was downward or upward. Here, in the upper left-hand corner, if the first motion was downward, this would be like a pull towards the epicenter, or basically a pull away from the seismograph station. On the other hand, if you look at the lower left-hand corner, if the first motion is up, this indicates a push away from the epicenter towards the seismograph station. So basically we're plotting as to whether the first motion was a pull or a push for each one of these different locations. Now the pull quadrants are color-coded blue, whereas the push quadrants are color-coded orange. And the boundaries of these quadrants can be represented by two lines, one occurring east-west, another occurring due north-south. This is the overall distribution of patterns that are expected for strike-slip motion or transform motion. And we have two solutions. The boundary going east-west can represent one fault plane. The boundary going north-south can represent a different fault plane. And the question is, which one of these two fault planes is the correct solution? Notice also that for the fault plane exhibited by the horizontal boundary, we can plot the sense of motion by putting the motion arrows directed towards the push quadrants. And what we see here is the relative motion along a strike-slip fault. In this case, this is a right lateral strike-slip fault. Does everybody see this? The second solution is also possible to pick which of those two fault traces is the actual fault trace. We have to know the geology of the area around the epicenter and note the general direction of the faults within that particular region. But based on fault mechanisms, we know that this was a strike-slip type of motion. For normal faults and thrust faults, the distribution of pushes and pulls are going to be quite a bit different. We'll get distinctly different patterns on these plots. But this is just for a strike-slip, this particular example. Yeah. Whether it's a push or a pull, you look at the seismogram for each of these different stations and just look at the pattern. In this case, the P wave shows the initial dip. So this is assigned a pull. On the other hand, in the lower left-hand corner, this P wave shows an initial spike. So that's assigned a push. And then you just simply plot up all this information from seismograms around the world and construct these graphs, and from there you can determine what type of fault actually produced the earthquake. This particular pattern comes up with 4 different quadrants and 2 potential directions of fault planes. But this pattern, this distribution, is known to be that for a strike-slip fault. If it was a normal fault or a thrust fault, the distribution pattern would be very different. Okay. Now we saw before that normal faults are associated with tensional stresses. They occur in brittle as a result of brittle response to crust that's stretched and elongated. And as we would expect, these normal faults are associated with divergent plate boundaries, mainly seafloor spreading ridges and continental rifts. Conversely, strike-slip faults occur where large segments of Earth's crust slip horizontally past one another, and these large strike-slip faults are known to occur along transform plate boundaries. For fault mechanism solutions along mid-ocean ridges, we find that mid-ocean ridges and these transform faults are characterized by very shallow earthquakes, or earthquakes that typically occur at depths of less than 4 kilometers. And the fault mechanisms indicate that along ridge segments we're looking at normal faulting, essentially tensional stress and normal faulting, whereas these transform faults that offset segments of mid-ocean ridge, we're mainly looking at strike-slip motion. On the other hand, reverse and thrust faults occur where crustal rocks are shortened and thickened. This is associated with compressional stresses and convergent plate boundaries, typically with subduction zones and in some cases continental collisions. Tsunamis, which are also known as seismic sea waves, are destructive waves that are often inappropriately called tidal waves. The term tidal is assigned to processes, events associated with the gravitational pull of the moon on the Earth, like the daily rise and fall of the tides. And so tidal waves are not a proper term for tsunamis. Now, tsunamis are generated several ways. For example, volcanic eruptions like occurred at Krakatoa back in 1883. Large undersea landslides triggered by volcanic eruption or earthquakes. And the third way is a vertical displacement along a fault located on the ocean floor. And in this case, we're looking at a subducting plate along a convergent plate boundary. And here we see that fault slippage pushes up a column of water, and that's what generates initially the tsunami wave. The wave out in deep ocean is actually almost undetected. It's a very, very low amplitude, very broad wave for the most part that does very little to no damage whatsoever. The problem with tsunami waves is when these waves start to approach the coastal areas. And notice that when the tsunami wave gets closer and closer to shore, eventually the base of the tsunami will start dragging on the shallowing seafloor. And once that happens, three things occur. One is that the wave height will dramatically increase as it gets closer to the shore. Another thing is that the wave will slow down. And the third effect is that the waves will bunch closer together. The wavelengths will become smaller. And all three of these effects occur as the tsunami wave encounters shallower and shallower seafloor. The ultimate result is that tsunamis can become very destructive once they hit the coast. Now this figure shows how tsunami detection systems operate within the deep ocean. Basically, we start out with a sensor on the ocean floor labeled 1, which measures water pressure. So changes in the water pressure is a good indicator that a tsunami has been generated. From there, the measurements from this sensor are sent by acoustic signal to a buoy located on the surface, and that's labeled 2. And then once that signal reaches the buoy sends a signal to a satellite, and from there the satellite sends a signal to an early warning station on land. Now, even just 15 minutes after an earthquake strikes, the warning stations can already determine the path and the strength of the tsunami. and as a result send out warnings to the endangered regions. These warning systems were not in place back in 2004 during that Sumatran earthquake, but I assume that since then the Indian Ocean has been equipped with many of these early warning systems. Now, the Great Tsunami of 2004 was associated with a magnitude 9 earthquake off of Sumatra, Indonesia, and this in turn sent a massive tsunami across the Indian Ocean. And along some coastlines, water surged several kilometers inland. The damage was most severe in Indonesia, Sri Lanka, and also in Thailand, where an estimated 230,000 lives overall were lost. So this map shows the epicenter of that December 26, 2004 earthquake that occurred just off the coast of northwestern Sumatra. This earthquake was associated with a major convergent plate boundary occurring just to the west of Indonesia. And from there, this generated that huge tsunami, which then struck the coast of Banda Aceh in Sumatra and traveled further west, eventually hitting Thailand, southern India, and even as far west as the east coast of Africa. This is the famous before and after picture of Banda Aceh after the tsunami. Now, as the tsunami approached the coastline, the water along the coastline first receded, and the unsuspecting tourists began to walk out on the newly exposed beach going, wow, this is pretty cool. But soon afterwards, the tsunami wave rolled in, and here in this photograph you can see the tourists madly racing back towards shore with this approaching tsunami wave that was even carrying boats towards the coastline. And those boats ended up on land on top of roofs. Yeah. So if you're ever at the Gulf of Mexico on Stewart Beach and start seeing the coastline recede, head in the other direction very, very quickly. Well, it depends on how fast you run, depends on how fast it hits, but for the most part, the people didn't realize what was about to happen. All they knew was that the coastline was receding, and they were pretty interested in this effect and started walking out into the newly exposed, expanded beach, not realizing that there was an approaching tsunami wave. Then there was that magnitude 8.9 earthquake that occurred near Sendai, Japan, back on March 11 of 2011, which quickly generated a 30-foot wall of water that reached as far as 6 miles inland. This map shows the travel times of the tsunami from the Japan earthquake back in 2011. And the color codes are an overall indicator of the size of the tsunami wave. The pinks and reds and oranges reflect the largest waves, and the greens are the wave sizes that are quite a bit smaller. But notice that the times are in scales of 3 hours, 6 hours, 9 hours. So obviously this is plenty of time for early warning systems to reach nearby coastal areas and give people plenty of time to evacuate the coastal areas. Here, for an example, this Japan earthquake, the resulting tsunami took more than 21 hours to eventually reach the west coast of South America. Okay, can earthquakes be predicted? Well, it depends on whether you're looking at short-range predictions or a long-range forecast. Currently, there's really no reliable method for making short-range earthquake predictions on the scale of hours, days, weeks, or even months. More reliable are these long-range forecasts, which give a probability of a certain magnitude earthquake occurring on a time scale of 30 to 100 years or more. There have been attempts at short-range earthquake prediction. For example, there were reports of animals behaving strangely just before an earthquake. Other bits of evidence were tilting and other types of ground deformation in an area of imminent fault slippage prior to the main shock. Increase in frequency of small earthquakes, foreshocks, prior to the main event. These were obviously detected using seismometers positioned in and around the area of the fault. The opening of microfractures in bedrock prior to the main earthquake can potentially change the physical properties of the rock, as for example changing the conductivity of electric current, changes in the overall P wave velocities of the foreshocks. Wells even exhibit changes in the water level and increased radon concentrations within the water, and this was attributed to opening of microfractures within the rock that in turn could potentially alter the groundwater flow and also release trapped radon gases within the rock into the groundwater system. But the point of it is that all of these different possible events could occur prior to a major earthquake, but the overall utilization of these findings has been quite sporadic and for the most part not very, very reliable. Scientists put more faith into what are called long-range predictions. And this involves what's known as paleoseismology, which is the study of past seismic activity. And this is used to predict probabilities of future earthquakes. For example, geologists and geophysicists can dig these trenches right along a fault zone, and by doing so they can decipher events and past earthquake activity by studying the displacement of sedimentary beds dating back many, many centuries and even thousands of years to get an overall record of earthquake activity along that particular segment. Another way of predicting is using what are called seismic gaps along a fault. Basically, these are segments where the fault is presently locked, such that strain along these segments is not readily released, and thus is anticipating to be building up over long periods of time. Now, when the fault eventually slips within a segment, within the seismic gap, we can expect an enormous amount of strain buildup to be released, and as a result, we'll likely get a major earthquake. Here, for an example, along the coastal area of Indonesia, known as the Sunda megathrust, these yellow areas are the fault segments that have been affected by relatively recent earthquakes. For example, the large earthquake that occurred off of Sumatra back in 2004 affected the region of the fault shown in that yellow region. Other segments were affected by other earthquakes that occurred, for example, in 2005, 2007, and so on. But notice there's a seismic gap within this white area. This area has not experienced an earthquake over the last few decades. So the prediction is that if there is going to be another, or probably when another major earthquake occurs along the Sunda megathrust, the probability is highest is that that earthquake will occur within that seismic gap. Only because there's probably a lot of seismic, a lot of elastic strain energy building up within that region that needs to be released. The San Andreas Fault of California is an active earthquake zone, probably the most well-studied of all the faults around the world. Now, displacement along the San Andreas occurs along discrete segments ranging anywhere from 100 to 200 kilometers long. Some portions exhibit slow, gradual displacement, which is known as fault creep. Other segments regularly slip, producing small earthquakes, and there are even still larger segments that are storing elastic energy for hundreds of years. And eventually, when these segments slip, they're going to rupture into these great earthquakes. This overall process is described as stick-slip motion, and it's predicted that the great earthquake should occur about every 50 to 200 years along these particular sections. As, for example, occurred along the San Francisco earthquake back in 1906. So here's the simplistic version of the San Andreas Fault. And notice that we have different segments that have different color codes. The blue segment on the north, at the north, was affected by the 1906 San Francisco earthquake, and that segment is presently predicted to have less than a 21% probability that a major earthquake will occur within the next 30 years. Further south, along the central segment, color-coded green, that segment is experiencing creep. And so fault creep diminishes the prospect of a major earthquake because of the frequent slippage that's occurring. And as a result, there's not a whole lot of strain energy building up before it's released by an earthquake. Further south in that orange segment, that segment was affected by the 1857 rupture that produced the Fort Tejon earthquake. That orange segment has a 60% probability of a major earthquake within the next 30 years. The segment of most concern is the southernmost segment that has not experienced a major quake in the last 300 years. That southern segment is the most likely source of the next major earthquake. And notice that that segment occurs due east of Los Angeles. Now, even though the northern San Andreas Fault has a less than 21% probability of an earthquake, that does not leave San Francisco off the hook, simply because there are additional faults around San Francisco area that can also rupture, and this in turn increases the earthquake probability. We saw that the San Andreas in the northern segment has a 21% probability of a major earthquake, but just to the east we have the Hayward and the Rogers Fault that has a 27% probability of a major earthquake. We had the Calaveras Fault further to the south with 11% probability, and even other faults indicated in yellow that have less than a 10% probability. If we include all these probabilities among all these different faults, the net result is that the San Francisco Bay region has an overall earthquake probability of 62% for a 1 or more magnitude 6.7 or greater earthquake occurring sometime between 2003 and 2032. Any questions? Anyway, this is how probabilities are assigned to different faults. It's based mainly on past earthquake activity. Okay. Here's an example of the sequential westward progression of large earthquakes along the northern Anatolian Fault in Turkey. Notice that back in 1939, the fault segment furthest to the east was affected by a 7.8 magnitude earthquake. And then in 1942, the segment further west was affected. Notice that overall, the segments progressively further to the west have been affected by more recent earthquake, so that what's happening is that the slippage along the northern Anatolian Fault is progressively advancing westward over time. The last major earthquake to occur was 1999 in Izmit. What's the next city that's going to be affected sometime in the future? Istanbul. Yeah. Based on the past history of slippage along the North Anatolian. Now, the U.S. Geological Survey constructs these seismic hazard maps of North America, and again, based on past earthquake activity. The red regions are the areas that can expect future major earthquake damage. The yellows, moderate earthquake damage. The greens and blues, minor earthquake damage. We fall within the gray region, so we don't really have to worry about earthquake damage to any great extent. But anyway, this is just something else that paleoseismology allows us to do. This is I-10 in California after the Northridge earthquake in the early 1990s. Kind of looks like I-10 in Houston. No, this isn't an I-10. This is Interstate 5. Sorry, this is North Interstate 5. Whew. I thought we were in danger there. Anyway, that's it.